Hey everybody, Dr. A here, and in this video we're going to be exploring an example of beam internal loading. So let's go ahead and get started. In the given information, we're being asked to determine the internal loads at point B using the method of sections. So here we have a simply supported beam. It's got a roller at A and an external pin connection at C. And the point B that we're interested in is right here. Now, there's no additional support at B, no internal hinge at B, nothing at all. This is a solid member. This is just a point of interest, point B, okay? Now, along this beam, we have a 200-pound load that's at a 60-degree angle, and then we have a 300-pound load that's right in the middle of the span. And you see that 200-pound load is 2 feet away from A, okay? So how do we go about solving this problem? Well, what we're going to do as we write solution is we're going to note that by method of sections, what do? Well, we pass a cut section through the point of interest, and then we look at a free body diagram of either everything on the left side of the cut or everything on the right side of the cut. Okay, so we're going to start out by making a note of the following. When using method of sections for this particular problem, we will need at least some of the external support reactions for this beam. And again, why is that? Well, remember, you pass the cut through the point of interest. That'll be point B. And then you look at a free body diagram of either what's to the left or the right of B. This is the right, actually. The right or the left of B, okay? Now, does it matter which free body we look at? Does it matter if we analyze the free body to the left of the cut or the right of the cut? No, you could look at either one. You'll get the same thing no matter what, but one of them might be a little bit easier to deal with than the other. So I'm going to make another note, okay? I'm going to say that the free body diagram to the right of B seems simpler to analyze. Then we're going to say to analyze it, we need what? We need CX and CY. Okay, so ultimately that's what we're going to need. We're going to need to get the external reactions at point C if we want to use this right free body diagram to analyze the internal loads at point B. Okay, now again, if we wanted to look at a left free body diagram, what would we need? We would need AY, okay? But again, we only really need what's happening at C if we look at a right free body diagram. All right, so let's do that. Let's go ahead and draw a free body diagram of the whole system first and solve for the reactions, okay? So I'm going to say begin with a free body diagram of the entire system to get CX and CY, okay? So I'm going to scroll on over and I'm going to say free body diagram FBD of entire beam, all right? So if I do that, I've got the beam here. I'm going to have an AY here, and I'm going to have a CY and a CX, and then I have the point load in the middle, and the point load at an angle, 60 degrees. Let me just double check I wrote everything right, and I did. And we have some dimension lines here, 2 feet, 3 feet, and in fact, let me write those a little bit better for us. So I've got 2 feet, 3 feet, and 5 feet here. Now, do I need to include point B on this free body diagram at this time? No, because I'm not really doing anything new yet. I'm not doing method of sections just yet. I'm about to, but before I do that, I need to get these externals first, which come from the entire beam, okay? So in order to do that, I'm going to start with sum of the forces in the x direction equals 0. And so I'm going to say 200 pounds times the cosine of 60 degrees plus cx equals 0. And then punching that through, that should be 100 pounds. And it comes out negative, so that means cx is pointing to the left, okay? Now I need ay and cy. So if I want cy, I'm going to say sum of the moments about point A equals 0, okay? And when I sum moments about point A, I'm going to break each one of these forces down one at a time and get their y components and then see what kind of moments are generated about point A, okay? So we know how to do this. That'll be negative 200 pounds times the sine of 60 degrees and then times 2 feet, and then minus 300 pounds times 5 feet, and then plus cy times 10 feet equals 0. So real quick, refresher on how we got to that point. We get the y component of 200 pounds. That's the 200 sine of 60. And then we say times 2 feet, which is its moment arm. And that's going to cause a counterclockwise tendency of rotation, which is why we have a negative there. We then do 300 times 5 feet. That's going to generate a clockwise tendency of rotation. Sometimes I say those backwards. Clockwise tendency of rotation, which is why this is negative. And then we're going to say cy, I'm assuming it's pointing up, times the full 10-foot moment arm. That's going to cause a counterclockwise tendency of rotation, which is why that's positive, okay? So I'm going to do some rearranging here, and I'm going to solve for cy. And let's punch that in our calculators. 200 times sine of 60 times 2. And then we're going to combine that with 300 times 5 and move it to the other side of the equation. Divide by 10. And so I get about 185 pounds, and it's positive, so it's reacting upwards. Now, do I need to get ay? Do I need ay? No, I don't need it, okay? Because when I do method of sections, we agreed earlier we were going to look at a right free body diagram, okay? Can I get ay, though? Could I get ay if I wanted it? Absolutely. You could definitely get ay if you wanted it, but we don't need it, okay? So now we're going to say use method of sections and analyze a right free body diagram, okay? And so here's what I'm going to do. I'm going to make a cut at point B, and I'm going to look at a free body diagram that is to the right of that point B, okay? Now, where is point B? Well, point B is given Point B is given 2 feet away to the left of point C, okay? So I'm going to go ahead and label that. That's 2 feet right there. And then what do we have going on at C? Well, we calculated that CY as 185 pounds going up. And then we calculated a CX of 100 pounds going to the right. And then what's happening at B? Well, I have some things that become exposed, right? So I'm going to have a shear force at B that's now exposed. I'm going to have an axial force I can call that NB, or normal force at B. And then I'm going to have a moment at B as well, okay? So what can I do? Well, now I apply equilibrium equations to this free body diagram, this method of sections free body diagram, to solve for these three internal loads. Now, here's a question for you. Do I know the direction of these three internal loads at B? Well, not really. I mean, we assume a particular direction. The typical sign convention is that positive shear causes the free body diagram to want to rotate clockwise. Positive moment might cause the beam segment to make a smiley face here, and then positive axial force will cause tension here. Now, did I assume the positive senses for these unknowns? No, I didn't, but I did for shear, but not really for moment or for normal force. Does it matter? Not really. I mean, we use the typical sign convention. So if I wanted to, I could say, you know what, I'm going to use the typical sign convention, and I'm going to put the positive moment here, which will cause this to bend concave upwards. And I could say, you know what, I want to use positive sign convention for axial load, and I'm going to make the positive axial load in tension. And then what'll happen if you run the calculation, something pops out negative, it's just going in the opposite direction, okay? So we have the sign convention, which is good to follow, but you still can get the final conclusion be correct if you assume the opposite, okay? Remember, if something comes out negative, it's just pointing in the opposite of what you initially assumed, okay? So here I'm going to say sum of the forces in the x direction equals 0. And so, again, if I assume NB is in tension, I know I just changed the sign, but that's okay. Then that'll be negative NB, and then minus 100 pounds equals 0. Do the calculations. NB comes out to be negative 100 pounds, which just means that it's 100 pounds in compression, which really means that NB is 100 pounds pointing to the right, okay? What about the shear force? Well, I'm going to say sum of the forces in the y direction equals 0. And so looking at that free body diagram of method of sections, I have VB plus 185 pounds equals 0. And so VB is equal to negative 185 pounds, which just means that it's shearing in the opposite direction, 185 pounds downwards, okay? And then finally, I'm going to say sum of the moments about the cut equals 0. Counterclockwise is positive. And so again, I'm going to sum moments about this cut point right here. So when I do that, I'm going to write negative MB, and then I'm going to say plus 185 pounds times 2 feet equals 0. So MB is equal to 185 times 2, so I get 370 pound-feet, and it came out positive, so this one is in fact rotating clockwise. So what are my final answers? My final answers are these three internal loads: NB, okay, VB, and MB. These are my three final answers. So, if this was like a homework assignment, you'd probably want to write a little summary and box that in as your final set of answers, okay? So that concludes this example of exercising method of sections for a beam to find some internal loadings at a point. Hopefully you found this helpful. If you did, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.